Okay, in Calculus AB, you have what's called the law of natural growth, which gives us the differential equation of just the rate of change of a population is proportional to the population itself. The BC model that we use for population growth, and let me actually first say, you still have the AB model, but now you're going to have the AB model as well as the more advanced BC model to work with. And the reason this isn't in the AB curriculum is because in order to solve the differential equation that we're about to look at, you have to have the technique we learned yesterday. And so you should remember how to solve this differential equation from AB. You're also expected to know how to solve the differential equation we're about to come up with. But I will say that at the same time, it's, well, never mind what I was thinking. Anyway, so the logistic model is beautiful and it's brilliant, absolutely brilliant. Because with the law of natural growth, you end up getting an exponential growth function. And how many times did you see that as a population model and just laugh at it? Because it's like, things don't continue to grow exponentially. I'm sorry, but that isn't reality. It's not reality. Now, we could maybe live in a pretend world where there aren't predators and prey. And oh my goodness, who could think of it? A world without war and disease. What? It could happen, maybe. You beat me to it. There is one thing that you cannot just pretend on. And that's, you can't pretend that we have unlimited space and supplies. It just is not reality. So, reading disease rules history. We are mere pawns of microorganisms. Okay. So, carrying capacity. Carrying capacity is the number of the population that an environment can sustain. And this model is, again, I'm going to say it is an absolutely brilliant model that kicks off the realistic version of population growth equations. From the model we're going to learn here, small things can be added on that do bring in realistic issues of predator-prey, that do bring in realistic issues of disease and war. But you actually need to start with the logistic model, not the model that's highlighted. So here we go. We need a second factor. And that's where this parentheses, what that parentheses is for, is to come up with a second factor. And I want you to see if you can figure out what it is, but we are limited in time. So here's what we need to happen. Now think realistically. If your population is actually equal to carrying capacity, tell me about your growth rate. If your population equals carrying capacity, your growth rate is 0. The only way to make this expression 0 is for my second factor to be 0. So if population is carrying capacity, then that second factor needs to be 0. Now, the next couple things are, what should you expect dp dt to be if you are over carrying capacity versus under carrying capacity. If you are over carrying capacity, tell me what your growth rate is different from being under carrying capacity. Yep, an issue of being negative versus positive. So I need dPdt to show up as negative if my carrying capacity is, or if my population is greater than my carrying capacity. That means I need that factor, the second factor here, to be negative under these circumstances. And I should have a positive growth rate if my population is under carrying capacity. That second factor needs to show up positive under that inequality. Now, the last two are looking at if you do have your population under your carrying capacity. There's a big difference between being just under carrying capacity and being like way under carrying capacity. If you are way under carrying capacity, then your growth rate should be exponential or close to it. But if your population is under carrying capacity, but almost carrying capacity, your dPdt is positive, but it's close to zero. It's a little bit bigger than zero, but not much. So that means that under the situation of barely less than, I want my factor to be near zero, but still positive. And then to be far less, for me to get that my population is actually just the piece that makes exponential growth, that means that this factor is near 1. And if you now kind of put it together, we don't want the second factor going bigger than 1. Having my growth rate show exponential growth is the best it's ever going to be. If I'm dealing with a population under carrying capacity, my second factor needs to be between 0 and 1. Now, I'm going to give you, I'm debating whether I should give you a hint or give you a minute to see if you can come up with it. Realize one thing that's really, really important is having a ratio with the population and the carrying capacity. And also later on, I'm going to show you that P minus C is actually in a certain format close to what we run into. It's just a slightly different form. So we want a formula here for this particular second factor that uses some kind of fraction with C and P. We don't want to go any bigger than 1. Yes. You got it. And just distributing the division of your C, that gives us 1 minus population divided by carrying capacity. Now, population divided by carrying capacity, if your population is under carrying capacity, but yet still positive, P over C is a number between 0 and 1. If your population is over your carrying capacity, your P over C is greater than 1. And if your population is so small compared to your carrying capacity that it's near zero as a ratio, then you're getting 1 minus near zero. So this is such a simple formula, and it's going to be even more amazing when I show you how nicely it integrates. But before that, I want to make sure that you know all the details you're expected to be aware of that go with carrying capacity. And also, by the way, I will be posting some of the work you see here on Google Classroom. And now was I wanting to go there yet? Not yet. This is where I wanted to go. I'm actually just showing you this much. Okay. So what you want to know is on an exam, you're going to be given a differential equation that represents the logistic growth model. You want to be aware of the different forms that it's going to show up in. All three of these are the same exact differential equation, just a different format. On an exam, you're typically going to see one of these first two. So I want to point out to you that you can tell them apart quickly by whether the second factor starts with a 1 or whether the second factor ends with minus population. That's a quick way to tell the difference between the most common way that this will be written. But they might give it to you in this format. And I just want to kind of prepare you for that issue. And one way that you can figure out the carrying capacity based off of this model is to just take whatever this is, factor it out, and you'll have left over a number and a p if you take whatever is here and rewrite it as p divided by some number. Carrying capacity is that number. Whenever you run into the logistic growth model, your first thing to do is find the carrying capacity. And when you're on a timed exam, you don't have time to mess around with the algebra of it, so you want to be prepared for finding it within the differential equation. Now, also, and this is directly from the AP course description, I have it in quotes, directly quoted from College Board. Be familiar with the phrase, the rate of change of a quantity is jointly proportional to the size of the quantity and the difference between the quantity and its carrying capacity, which is what this is showing. And it's like you got to read that a few times. That phrase could show up on the AP exam, and if you're familiar with it, logistic models are always very easy problems. If you know what you're looking at, they can go super quick. For example, if you know you have a logistic model and you are asked what is the limit as time approaches infinity of your population. Now, I've got to say something though. There are actually two possible answers for the limit as time approaches infinity in your population. What is the other technical answer that could show up? 0, correct. So when they give you, if they ask you about the limit as time approaches infinity of your population, they have to give you some initial value. Otherwise, you don't know if you even have a population to begin with. So be aware that when they give you initial population values, you may not actually need to use that number, but you need to have a number in order to say that this thing actually grows. They will never give you an initial population of 1, because then that leaves the question of, is this something that can reproduce asexually? And that's not up to you to figure out. So they're never going to do that to you. And they're also not going to throw at you like the population is 2 for you to go, well, are they 2 that can procreate together? You know, they'll give you enough of a size that you can assume that it is a reproducible population, even though they don't have to directly tell you that there are boys and girls who can reproduce. They don't need to go through that explanation. So just know that's what to expect. Now I'm going to go back over here, because this is another thing you're expected to be aware of. We're going to find the second derivative of the population with respect to time. And we're going to start with this version, because that version is already having the multiplication through, because we don't want to do product rule. Nobody wants to do product rule. They can avoid it. So I've got KP, and now I already forgot, minus K over C times P squared. Okay. If I'm going to find the second derivative of population with respect to time, I have to differentiate with respect to time. In here, my only variable is P, and P isn't time. So I have to differentiate implicitly. So I am going to ddt both sides of the equation. On the left, that gives me my second derivative. And now, an unknown constant times P, take the derivative. That unknown constant times, and then the rate of change of P with respect to T. Minus constant multiple. And now I have a full-on chain rule going on. So I have blah squared. I take the derivative of the outer function, which is blah squared. The derivative is 2 times blah. Shove the function in, multiply by its derivative with respect to time. So implicit differentiation, it is very, very important in BC calculus that you become more aware of implicit differentiation. It's going to show up more often for you. Always be concerned with who your variables are and who you are differentiating with respect to. Now, if I want to look at where the population model is growing at an increasing rate versus growing at a decreasing rate, I want to know first, when is the second derivative 0? So what can I factor to the side as I solve for 0? With this minus sign right here, what do I have in common that I can just factor out? And then that leaves me with a 1 minus 2p over c. Now, The number K is the proportionality constant of that particular species as far as the proportionality constant of how quickly it grows. It's going to be a positive number. Otherwise, if you've got a population that's only decreasing, I think we've got a problem, and we might as well not even talk about this population because they're going to be extinct soon anyway. So, K is positive. Now, dPdt, it's positive or negative depends on whether I am above carrying capacity or under carrying capacity. However, the way that this is worded, this says that it's growing. If it's growing, then I'm dealing with a positive dPdt. That means it comes down to this expression. So first, we want to solve for population and find out what about the population causes the second derivative to equal 0. And now think about what that is saying. When population is at half of its carrying capacity, you change from growing at an increasing rate to growing at a decreasing rate. Now, to really put that into context, think about what's going on if you are at carrying capacity. If your carrying capacity, your growth rate is 0, that means your birth rate equals your death rate. That is a horrible situation, one that I hope none of you or your future has to deal with. That's horrible. Reaching half the carrying capacity is not pleasant. If you're a population, you want to be growing at an increasing rate. You know, if you begin growing at a decreasing rate, things aren't going fantastically. And if you think about what carrying capacity really means, carrying capacity means that quantity of people is having just enough to eat to stay alive. That's very different from comfortable. That is always the fun question. There have been a lot of speculation about carrying capacity for humans, but the hardest thing about it is we affect our environment so drastically that no other species does. It makes it far harder to determine what our carrying capacity is because it's actually changing and we are affecting it. I don't want to think too hard about that. Okay. So back to just the mathematics of the model. If you reach half your carrying capacity, you're reaching a point of inflection where you change from a concave up to a concave down. And you need to be aware of that. So the thing that determines where population is growing the fastest is really when your population under half your carrying capacity or over. Now, when problems like this have been asked on AP exams, they usually give you an initial population that is under half the carrying capacity so that it has not yet reached the point where it is growing fastest. And so if you begin your population under half the carrying capacity, and you are asked what is the population when it's growing fastest, just take your carrying capacity, divide by 2, and go, whoopoo, done. No explanation even needed, because you're expected to know this model well enough to realize that. I'm going to now show you a slope field, which will also bring out visually what was found. Okay. So take a look at this slope field. The x-axis is time, the y-axis is population. Can you tell the carrying capacity? Yep, 1,000 is the carrying capacity. And now, what is half of 1,000? Right, 500. If you look at that horizontal line at y equals 500, do you see that that is the steepest of the slopes? And another thing you should notice is that if you take any row, you have identical slopes across the row, because the rate of change of population isn't dependent upon time. It is dependent on the quantity of your population based on an understanding of where carrying capacity is. When you look at the differential equation that goes with this, so I'm going to head back over there to show that. All these differential equations do not have time involved. They are based solely on population. And I'm going to now show you 3 solution curves in this slope field. And what you have is, if your initial population is 100 when your carrying capacity is 1,000, you're first increasing at an increasing rate. So you are heading up and you are concave up. You can see there's a point of inflection right around there. While you are still increasing the quantity of your population, you are doing so at a decreasing rate. And as long as you have enough initial population, all roads lead to carrying capacity. If for some reason you were asked when is population changing most rapidly, and your initial population isn't under half carrying capacity, it's that initial moment, because it the growth rate becomes less steep. Or I should say, if you look at the slope field, it is less steep as you head toward carrying capacity. Now, the next thing we are going to do, actually, before I say this, everything that you really need to know on the AP test is right here. And I'm going to post that onto Google Classroom later today. But now I'm going to go over with you something that, while the AP test says you should know this, it's very hard for them to actually test you on it. But you are expected to know how to find the general solution to the logistic differential equation. That's why this doesn't show up in the AB class. So I'm going to go through this with you, but there are going to be some moments where I talk about some choices in algebra manipulation that you wouldn't necessarily think to do. So here we go. We want to solve a differential equation, and this is a separable differential equation. So we're going to multiply the dt over to the right, and anything that has p needs to go over to the left. So let's do that. Oh, oh my goodness, yes. And let me not make the same mistake I made first period. I took the screenshot of this from the textbook. Do you notice they have a lowercase k and a capital case K? Do you know how much that messes us up? I write the formula with a C for carrying capacity. I don't know why the textbook decides to use a capital K, but when I was doing this first period, I messed up because suddenly they were both the same K. Because that's what happens when you use a lowercase and an uppercase with the letter K. So I need to change that to C. It will save problems. Who wants a fraction in a fraction? No one. So what right now I'm about to do an algebra move that you wouldn't necessarily think to do, but once you see it, you realize that's going to make life easier. To not have a C in a denominator in a fraction, I'm going to multiply top and bottom by C so that I can distribute the multiplication of the C through that parentheses and no longer be in fraction land. So that makes the numerator C and the denominator is now the P that is right here times, and when I distribute the C over this parentheses, C minus P as I distribute. So this is an important place to notice doing a step you wouldn't necessarily think to do. Now it's set up ready for integration. I'm going to integrate the right side first because it's nice and simple. What is the integral on the right side? Yep, kt. Now, when I put my unknown constant, I don't want to put plus c. I think that's why the textbook used a capital K. But what I'm going to do is I'm going to put plus, and I'm just going to use a letter. All right, I'll use the letter A. Actually, no, because of what's about to happen. I think maybe if I use like a capital W, it's just a letter we're not going to be using, and we don't associate it with other things. So this is my constant of integration. Before I integrate the left side, I want to realize what I've got going on. My only variable is P. C is a constant. And do you see that we need to use fraction decomposition? So I'm going to take that fraction and play with its algebra over here on the side. And this is why I didn't want to use the letter A. I need to find the constant above P and the constant above C minus P. The first step in fraction decomposition is to multiply both sides by the common denominator. So on the left I have C, on the right I have A, the P's cancel, times C minus P, plus B, the C minus P's cancel, times P. And it's important, there are so many letters going on here that you've got to remember who the variable is. The variable is P. And when you're trying to find your unknown constants here, you need to take the variable and set it equal to something. And what you're looking at are, it's going to be easiest if you use the zeros of the two linear factors. So one of those zeros is p equals 0. The other 0 is p equals carrying capacity. So now when I plug in p equals 0, I get c equals a times c plus 0. Hey, well, how is that coming out so simple? This right here adds to the beauty of the differential equation they came up with. Not only did they come up with a simple second factor to become realistic, the integration is pristine, which is not normal. Moving on, if I replace my p's with c's, I will get c equals 0 and then b times, replace that p with a c. And oh my goodness, b is 1 as well. What the heck did my computer just do? And beautifully, b is equal to 1. Just too pretty. Now I'm going to rewrite the integrand 1 over p plus 1 over c minus p, and we're going to integrate. So first we get natural log of absolute p. We technically don't need the absolute values on there. But be careful with the next integral. It's easy to make a minor little mistake. I am going to actually, with this to the side, show an integration of this alone. I need to do a u substitution. The derivative of u with respect to the p variable, remembering that c is a constant, that derivative is -1. That means that when I multiply dp over to the right, I can also divide or multiply the negative over to the du, so that dp is replaced with negative times du. And then I'm going to emphasize that my dp was replaced by du times -1, but I pulled that -1 out of the integral out of habit more than anything. That means that I'm getting negative the natural log of the absolute value of u, where u is c minus p. Now this one, I do have to keep that absolute value around c minus p because the model includes population being greater than carrying capacity. So I'm now going to write, oh, I'm hearing my 10-minute reminder go off. So this is the result of integrating. And now I'm going to use the magic of doing things online. Lasso and move. I really wish it would move faster, but I'll be patient. If it moved faster, I'd end up going back and forth probably forever, and that wouldn't be fun either. Okay, there we go. Now we have solved the differential equation, but we have not solved for p as a function with respect to time. That's our next step. Now, I'm going to Actually, let me say this. Do you see what is going to be the next big thing? Log rules. However, if I do the log rule directly right now as is, I'm going to get P divided by C minus P. This algebra is not as pleasant as this algebra. So you can either reciprocate after condensing or multiply both sides by -1 first. And it's probably easiest to see the logical process if you multiply both sides by -1 before bringing the log rule in. So I'm going to erase that. And this is that star moment of you wouldn't really think to do this, but it makes your life a lot better if you do. When I multiply by -1, that's going to reverse the subtraction order. And then over here, I'm just multiplying by -1. While I could change this right now, I'm not going to. Now, condense your logarithm. And the reason this makes algebra so much easier, distribute the division of P, and suddenly you no longer have 2 P's, only 1. And that is going to be a much easier algebra problem to finish. My next step is undoing the logarithm by e to the powering both sides. The natural log and e cancel each other out, leaving me with absolute value of that. And I want to make sure to clarify, I've got in the exponent all of this. And this is where I want to make my move of using the exponent rule. The exponent rule of if you have the same base and you're multiplying, you add the exponents when you compress it into one exponential. Again, you're used to looking at this rule starting here, going to here. So you're having to think backward through that exponent rule. Then additionally, the absolute value is the same thing as plus or minus. And then we're going to just bunch up everything that is going to turn into just one unknown constant. If w is an unknown constant due to integration, negative w is unknown, e to the negative w is unknown, and whether it's positive e to the negative w or negative e to the negative w is unknown. So we're just going to replace that with a letter. But we are having trouble with letters and running out of them. The textbook uses the letter capital A at this point, but I can use a different letter other than A because we did use a capital A over in the fraction decomposition. We've used B and C. Did we use D? I don't remember, but D's kind of too close to P when you're writing by hand. Oh dear. So let's see, what letter shall we use that we can nicely distinguish? Ooh, I like it. I like it. That's a distinguishable letter that we haven't used. So C over P minus 1 equals some unknown H, and I'll use capital, but you can use your own letter as well. And now, this is quick. Blink and you'll miss it. Add 1. And then reciprocate. And then multiply both sides by C. And you have the solution to that differential equation. And I want to point out this is not a solution equation you would just come up with, but the differential equation was very logically obtained. So there are times where modeling behavior is easier to do with a differential equation. And that's where we really need math to come in to take that differential model and find a actual solution model. I want to also clarify that this is an unknown constant due to integration. That constant can be found by knowing an initial condition. Other than that, C is your carrying capacity, K is your constant of proportionality based on that exponential model. And either they give you those numbers or they don't give you those numbers. But be familiar with the format of this solution. Because, oh my gosh, okay, I suddenly got distracted. I'm not going to let myself get distracted. So there we go. And I will post some stuff up and I'm going to stop recording.